Hello, welcome to a video on the inverse trigonometric functions. So what we're going to be looking at here are inverse functions for the trig functions. Alright, now you may be thinking, oh, I can already tell this doesn't have an inverse function if you remember your properties of functions that have inverse functions. And that's true. First of all, let's go through this. This is sine. How do I know this is sine? It has that wave pattern, okay? And the other functions, the trig functions we looked at, tangent, cotangent, secant, cosecant, they didn't have that wave pattern. They had asymptotes and they went off to infinity. Sine and cosine were the only ones bounded between -1 and 1. So it's got to be sine or cosine. And then this is sine because it goes through the origin, passes through the origin, and it starts on its midline at 0 and it goes up and then down. So this is the sine function. Now, this is a sine function. First of all, it's a function. The sine function is because it passes the vertical line test, if you remember that from algebra. So the vertical line test says that a function can only have a vertical line intersect at one time at any point on the graph, alright, at every point on the graph. But the sine function does not have an inverse function as it stands across its overall domain because it fails what we call the horizontal line test. Right? The horizontal line test, if you recall, says a function that has an inverse function, or a function that has an inverse function, can only have a horizontal line pass it one time. You know, it can only intersect a horizontal line can only intersect the function once. Just like a vertical line can only intersect it once to pass the vertical line test. Well, here we see, because this is what we call a periodic function, it just keeps doing the same wave over and over and over and over and over again forever. This thing would intersect a horizontal line an infinite number of times. So because of that, a trig function itself cannot have an inverse as it stands. All right. If you also recall what we end up doing with these things to find their inverse functions, if you will, when they do have an inverse function, is we take that graph and we flip it over the line y equals x, which basically rotates it 90 degrees and then flips it horizontally. So if we take this thing, rotate it 90 degrees, and then flip it horizontally, we get something that there's absolutely no way that thing could pass the vertical line test. So its inverse, which would result, this would always result in an inverse. The inverse is not a function. The inverse no longer passes the vertical line test. Okay, so this is not the sine function, the cosine function, all of them, because they have that periodic nature. They're all going to fail the horizontal line test, which means they don't have inverse functions. Alright, so, well then how are we calling this section inverse trigonometric functions, if that's true? Well, it's because what we're going to do is we're going to slice the sine function up in a way that we do not have that repetitive nature. We don't fail the horizontal line test anymore. Okay, now there's multiple ways we could slice it. We could slice it right here and then slice it here, and now a horizontal line would only pass through it once. So that's from positive pi over 2 to 3 pi over 2. Okay, are those two places that I'm going to say, all right, from there to there is the only place the sine function exists. And if that's the case, then yeah, we do have a horizontal line test that passes. It only hits the graph one time everywhere. But again, if you remove those restrictions, meaning from here to here, then that no longer works. You know, you fail the horizontal line test. So that's what I mean by slicing it up. We're going to come up with a domain where we hit every y value, meaning we hit -1, we hit +1, and all the numbers in between. But a further restriction is we want the x's to be as small as possible, meaning we don't want to go out to positive pi over 2 and 3 pi over 2 if we can find something closer to 0 that will work. And what it ends up being here is we create our domain around, let me do this, negative pi over 2 to positive pi over 2. Right? And then it's like everything beyond that on the left and right don't exist. It's like these are the only parts of the graph that we're going to be dealing with. The only part of the graph that we're going to be looking at is between negative pi over 2 and positive pi over 2. Right? That's the smallest distance in absolute value that we can move away from the origin and hit every possible y coordinate that sine could produce. So if we make this restriction on the sine function, then we hit every single value from between negative pi over 2 and positive pi over 2. We hit every single value of the sine function between these two numbers. We run the gauntlet. You'll hear me refer to that as running the gauntlet, meaning hitting every possible y value we can hit. And we pass the horizontal line test now. A horizontal line only intersects this thing one time for the entire graph. Okay? So we restrict sine from the whole entire period, the whole entire domain of all real numbers to just negative pi over 2 to positive pi over 2. So we only hit negative 1 and 1, every number in between, just one single time. Now if you remember with functions, with function notation, f of x was the name of our function. Our inverse function we called f inverse, and we used that notation. Well, here we're saying sine of x is our original function that has this domain in this range. So all we're going to do is put this little negative 1 above the sine, and that will be the notation for the inverse sine. All right, inverse sine, or it's more formally known as the arcsin function. All right, all the trig functions, when we talk about their inverse functions, we're going to call it arcsine, arccosine, arctangent, arccotangent. We just put the arc in front of the original name, and we're dealing with the inverse function. Now remember, how do we get an inverse function from the original? How do we get the points? Well, any point that's on the graph of the sine function, so that's some point AB, then BA, flipping the x and y coordinate around, will be on the arcsine function. So if AB is on the sine function, then BA is on the arcsine function. So let's think about what that's going to look like. So here is the point negative pi over 2, negative 1. All right, that's a point on this. So that means negative 1, negative pi over 2, flipping that around, is going to be on the arcsine function. And pi over 2 and 1 is on this. So if I flip it around, I'll have 1 pi over 2. So negative pi over 2 was the smallest x, positive pi over 2 was the biggest x, negative 1 and positive 1 were the smallest and biggest y's. If you flip those around, the x becomes the y becomes the x. What we're going to end up seeing, the domain for arcsine, is going to be the old range of the sine, because we're flipping x and y coordinates. So the domain of arcsine is negative 1 to 1, and the range of the arcsine function is the old domain of the sine function. So from negative pi over 2 to positive pi over 2. Alright, so let's think about what this means. What did the sine function take in before? It took in an angle measure. Remember, we gave it an angle measure and it spit out the old y coordinate on the unit circle. Okay, so Here's the unit circle. We fed it an angle measure, and it said, okay, that's y coordinate. That y coordinate comes from that angle that you gave me. All right, that's what the sine function was. Right now, then what does the arc function, the arcsine function do? Well, look at the outputs, the range of the outputs. Negative pi over 2, positive pi over 2. Those are angle measures. So what does it take in? The arc function, the arcsine, takes in a y coordinate. You feed it a y coordinate. So here's the input, and it says, oh, well, here's what angle was needed to give me that. Okay, now here's the downside, here's the problem. There's always these limitations because we didn't go beyond this little window right here. The problems start coming in with arcsine. What if I fed it this y coordinate right here? Can it say that this is your angle? No. Why not? Because it can only give me anything between negative pi over 2, which would be down here, and positive pi over 2, which would be up here. So it can't give me this angle that's beyond pi over 2. Well, what would it give me? Well, look at the drawing. I give it a y coordinate somewhere between negative 1 and positive 1 because those are the only possible y coordinates. And it spits out the angle between negative pi over 2 and positive pi over 2 that has that y coordinate. So does this y coordinate exist anywhere else? Yes, it exists over here. So I'm going to call this x2y. So what is it going to give me? It's going to give me this angle. So it's going to give me this little acute angle that produced that. So that's the downside of using these arc-trig functions. Arcsine can only spit out quadrants 1 and quadrant 4. In quadrant 4, it'll actually produce negative angles. It won't even give us positive angles down there. So we have to understand, because of the fact that the sine, the cosine, the tangent, all these things are periodic and they wave. They never pass the horizontal line test. So we have to come up with a small little snippet of the original domain to get them to pass the horizontal line test, so we can even come up with an arc-trig function. So we can come up with an arcsine or an inverse sine. Alright, so here's what the inverse sine is going to look like. Okay, it looks kind of similar to what we had before, a little bit. It's just, again, like we said, this was our original sine function in that tiny little window we talked about. Remember, we said it's been rotated and then it's been flipped over the x-axis or y-axis, sorry, horizontally. And that's where this is coming from. So there's the 1, the pi over 2, the negative 1, the negative pi over 2. So it's been rotated and flipped to be able to get what we're seeing here. Okay, but notice now the domain of the arc sine function, or the inverse sine function, is the range of the old sine function. And now the domain of that restricted sine function is now the range of the arcsine function. This is always going to be the hardest thing to wrap your brain around, is that it only produces the output of the arcsine function, only produces quadrants 1 and 4. Right, and in 4 it's negative. Right, so these are just acute angles. It cannot produce an obtuse angle. We can't get an angle bigger than 90. It's either a negative acute angle or a positive acute angle, depending on which quadrant it falls in, 1 or 4. Alright, if we want to find an exact value of arcsine, typically they're going to give us these known outputs of sine, like the square root of 2 over 2, a half, the square root of 3 over 2, and some multiple of those. We have to think about the unit circle, okay, and think about where did I see this y coordinate? Remember, these are y coordinates. So where did I see this y coordinate? Alright, so this question is saying, find the exact value of the arcsine of the square root of 2 over 2. So it's saying go back to your unit circle, and where do you find this y coordinate in quadrants 1 or 4? Where do you find it? Alright, where do I find that as the y coordinate? There's the positive square root of 2 over 2. Alright, that's right there. It's in quadrant 1 because it's positive. Alright, to be a negative y coordinate, that means you have to be down below the x-axis, so that would be quadrant 4. So quadrant 1's positive, quadrant 2's negative for arcsine. Alright, so there it is, and that corresponds to positive pi over 4. So what's the exact value of this? I'm in quadrant 1, so there was a 45-degree angle, or these are going to typically be answered in radians. Pi over 4 is my value. That's between negative pi over 2 and positive pi over 2. Alright, for inverse cosine, it's a little bit different because between negative pi over 2 and positive pi over 2, if you notice, I only have positive values for cosine. And remember, that's because of the unit circle. Right? Between negative pi over 2 down here and positive pi over 2 up here, on the unit circle, the x's are all positive. Right? Because we're to the left side of the y-axis. Remember that sine and cosine are defined on the unit circle. So I don't have any negative values. I can't get to negative 1 between negative pi over 2 and positive pi over 2. So to get to the negative values, the negative outputs, I have to go beyond, beyond negative pi over 2 or beyond positive pi over 2. And so because of the symmetry, I could either go from 0 down to negative pi, or I could go from 0 up to positive pi. So just make the numbers easy to work with. We minimize negatives if we can. So we're going to use from 0 to pi, we're going to use these values to define the section that we're going to cut up the cosine function to be able to get all the outputs of cosine. So for the purposes of coming up with an inverse cosine function, the domain of the the cosine function is from 0 to pi, and the range is, again, the gauntlet. It's all the values that we could get, so negative 1 to 1. So that means if we're dealing with arc cosine, then the domain is going to be the old range. We take in negative 1 to positive 1, and what do we spit out? We spit out the angle that produces those x coordinates from the unit circle. Remember, now we're dealing with x coordinates because this is cosine. So before, you give me an angle, and the cosine function would give you the x coordinate that corresponded to that angle. Alright, well now we're just reversing the roles. Now we don't know the angle. All we know is an x coordinate. Alright, the cosine of some angle is this number. We don't know the angle. What is the angle? So this thing is unknown, and that's what arc cosine does. It says, alright, give me the x coordinate. Because it's an x coordinate, arc cosine will find the angle that produced that x coordinate. But again, the restriction, where do the angles live? They live between 0 and pi. So they live in these two quadrants. Quadrants 1 and quadrants 2. Oops. Quadrant 1 and quadrant 2. We can't have an angle that goes all the way down here into quadrant 3. Now why is that? Why can't I feed it this angle? Because it's beyond pi. Again, we would go beyond 1 revolution and we'd have multiple values that could give us that. So what would it return if I said, hey, this is the angle that I want. That's a y1, by the way, x comma y1. It's going to give me this point up here that has the same x coordinate as this one down here had, but it has a different y coordinate. So this is the angle that it'll feed me, or give me. And then if I'm in quadrant 3, then I'm going to have to figure out a way to adjust to get down here to get this angle, which we'll talk about in a little bit. So here's the little part of the cosine function we're dealing with. If we rotated that 90 degrees back and then flipped it horizontally, we would get this graph, where -1 is the smallest value that corresponds to pi. When -1 goes in, pi comes out. All right, and then when 1 goes in, right, 0 comes out. Right, because 0, 1 was on this, 1, 0 is on this. Pi -1 was on this, -1 pi is on the graph of the inverse. And all the points in between. Pi over 2, 0, 0, pi over 2. Okay, so it's just, again, a rotation and a horizontal flip to go from this graph to this graph. All right, so same thing as before. If we want to find the exact values of an arc cosine, you just think about, where do I see this x-coordinate? All right, so where is the x-coordinate? The square root of negative square root of 3 over 2. So bring in the unit circle. So where do I see the negative square root of 3 over 2 for an x-coordinate? All right, well, I see it right here, and I see it right here. All right, both of these have that same x-coordinate. All right, that x-coordinate goes up, the x-coordinate goes down in the unit circle. Which one of these two angles is arc cosine going to give me? Is it going to give me 5 pi over 6 or 7 pi over 6? It's going to give me 5 pi over 6, because again, arc cosine is only defined in quadrants 1 and 2, between 0 and pi radians. All right, that goes back to this little picture that we had right here. All right, it's only defined between 0 and pi radians. So where do I get the negative square root of 3 over 2? Back here, that would be, almost -1. That would be like down here somewhere. So that would correspond to -8.6. That would correspond to almost pi. And again, we see right here, we're almost to pi. We're at 5 pi over 6, but we're not beyond it. Okay, so it can only give me angles in quadrants 1 and 2. So for the purposes of arc cosine, again, it's like none of this stuff down here even is there. It's like it's all of that's gone. So think of it being completely blank down there. So for purposes of arc cosines, these are the only two quadrants that exist. So it's only going to be able to output these angles between 0 and pi radians. Okay, again, typically we don't look at the degrees here. All right, so 5 pi over 6 is our answer. You can see it from this table up here. All right, negative square root of 3 over 2 is at 5 pi over 6. But I would just practice using the unit circle for this, because of the fact that you should already have one. So if you have the unit circle, just look for that. But remember, you're in quadrants 1 and 2 for cosine, quadrants 1 and 4 for arcsine. All right, arctangent, same thing. We got this repeated pattern. If we did a horizontal line, it would fail the horizontal line test because we just keep hitting the same thing over and over. So we want to find the smallest set of values closest to 0 as we can that runs the gauntlet for the output of tangent. The output of tangent is -infinity to infinity. So in between every single set of asymptotes, we do that. So the closest one to 0, the closest one to the origin, is going to be negative pi over 2 to positive pi over 2. So that's the one that we're after. So that's going to be our domain, negative pi over 2 to positive pi over 2. The range is -infinity to positive infinity. So for arctangent, remember the domain was the old range. The old range is -infinity to infinity, and the range of the arctangent is the domain, the restricted domain. So we could actually have a inverse function. So negative pi over 2 to positive pi over 2. And notice this time we are restricting this because we do have vertical asymptotes here. So we do divide by 0. So we have parentheses, meaning those parts are not there. Okay, to arctangent, same as before, it's in the original unit circle. If we go back to, what is it that we're actually doing here? What does it mean? If we go back to the original unit circle, remember the original tangent function said where if I gave you a point, or I gave you an angle, the tangent would give you the slope of that angle. The slope of that line segment at that angle. Okay, so positive slopes here, negative slopes down here. Well, arctangent says, give me the slope. You input the slope, and it will output the angle that gives you that slope. So the slope is positive 4. What angle makes the slope positive 4? The arctangent of 4 will give me that angle. Alright, if the slope is negative, if you have a negative slope, that means you're down here somewhere. So instead of returning the positive angle that goes all the way around to here, it's going to return that negative angle that would go down from the positive x-axis. Alright, so if the slope is negative, then it's going to return a negative angle. If the slope is positive, it's going to return a positive angle. Alright, what if I feed it some angle, or if I feed it some slope, some negative slope, but I want to be in quadrant 2? Well, again, look at the range of arctangent. It's between negative pi over 2 and positive pi over 2. So it's between here and here. It cannot give me this angle. It can't go into quadrant 2. So it's only in quadrant 1 and 4 again, because of that range. So what's it going to do? It's going to go straight through on that same slope, because it's dealing with slope, and it's going to give me this angle right here. Let me kind of color code it a little bit better. This angle down here is the angle that it's going to feed to me. Alright, it's going to give me that. It's going to be a negative angle because down in quadrant 4. How would I find this positive angle right here? Well, we'll see in a little bit. We'll add pi to that. Alright, adding pi to that gets me back up here. It's just initially, because that's the way trig functions work. If we're not in the quadrants where it's defined, we have to do a little bit of an adjustment to be able to find the angles that we actually desire. Alright, so here is the arctangent function. So the arctangent function's domain, all real numbers, range negative infinity to positive infinity. Now remember, the arctangent function is the inverse of the tangent function, and vice versa. The tangent function on that range is the inverse of this function. So what does that mean? It means this function has an inverse. So to have an inverse, you have to be what's called a one-to-one function. Now what does it mean to be one-to-one? That means every time your x coordinate changes, you get a unique y coordinate. So every different x produces a different y. Alright, now why is that so important or so phenomenal or so amazing here? Well, it's because the domain of the arctangent function is all real numbers, every single possible value that exists. And the range is this tiny set of numbers right here, between negative pi over 2 to positive pi over 2. Alright, so to really blow your mind, what we're saying here is that the entire real number line from negative infinity to positive infinity all of that and all the numbers that are on there fits right there. So let me say that again. All of these numbers from negative infinity to positive infinity, all of those numbers fit in between two numbers that are actually on the line and that make up the line that they're part of. So this whole thing goes beyond negative pi over 2 and positive pi over 2, but the amount of numbers, the number of numbers between negative infinity and positive infinity is the same as the number of numbers between negative pi over 2 and positive pi over 2. Right? And as much as you may not believe that or disbelieve that, right beside you is proof. Right beside this conundrum, this paradox, is the proof that it's true, because we have a one-to-one function that takes the domain of all real numbers and maps them or sends them uniquely between two numbers on the number line. Alright, and then finding exact values, again, I would use the unit circle for this, and hopefully you added tangent to that unit circle. Alright, if you did, then you'll know this was the square root of 3 for tangent, this was 1. This was 1 over the square root of 3, which is the same thing as square root of 3 over 3. Alright, and because of that, this is the negative versions of those. This is negative square root of 3 over 3. This is negative 1. This is negative square root of 3, because this is steeper than this. So the absolute value of the number is bigger for the steeper ones. Alright, and then since this is negative square root of 3, we're on that same path. This is negative square root of 3, and so on and so on and so on. But we want to find where's the exact value of the arctangent of the square root of 3. So that's wanting to know what angle has the tangent equal to the square root of 3. Well, for it to be positive, that would be either here or here. This will also have a tangent of the square root of 3. But because this is down here in quadrant 3, and arctangent is again only defined between quadrants 1 and 4, the one that we're after is this one. So pi over 3, or the arctangent, is what our answer is. So again, we can see it without having to use the unit circle on this. I want the square root of 3, so that's here, so that corresponds to pi over 3, so that's our answer. But I would prefer you to get used to it on the unit circle, since you should already have one of those.